Let's look at some examples of ideals in commutative rings. Recall that an ideal is a subset of a ring R such that if X is in I and R is in R, then Rx is also in I. So it's closed under multiplication by elements in R. Okay, and there's a way to construct new ideals from old. First is addition of ideals. So if I1, I2 are ideals, then you define I1 plus I2 to be the set of all x1 plus x2, where x1 is in I1 and x2 is in I2. It's not difficult to show that I1 plus I2 is again an ideal. And then there's intersection of ideals. If I1 and I2 are ideals, then I1 intersect I2. This is the set of all elements x such that x belongs to I1 and x belongs to I2. This is again an ideal. Okay. Now we look at some examples of rings where we can classify all the ideals. So the first example, fix a field F and a set X. Let's say finite set. And let f box x be the set of all functions f from x to f. Now this is a ring under pointwise addition and multiplication. So if you have f1 and f2 in fx, then you define f1 plus f2 of x to be f1x plus f2x, and you define f1 f2 of x to be f1x times f2x. And under this these operations of addition and multiplication, fx becomes a ring. Now let me give you some examples of ideals in this ring. So if M is a subset of X, define IM to be the set of all F from X to F such that f of x equals 0 for all x in M. So this is the set of all functions whose restriction to M is identically 0. Now if you have a function which vanishes on M and you multiply it by any other function whatsoever, then the product will again vanish on M. So this is an ideal. In f of x. Okay, and here's some fun stuff. So if you take im1 plus im2, so a function that vanishes on m1 plus a function that vanishes on m2, well, it will definitely vanish on m1 intersection m2. So what this gives is im1 intersection m2. This is not difficult to show, and I leave it for you to think about it. And if you have im1 intersect m2, im1 intersect im2, so a function which vanishes on m1 and which vanishes on m2 is an element of I M1 intersect I M2. So that's going to vanish on M1 union M2. And what's more, if M1 is contained in M2, then this is equivalent to saying that I of M1 contains I of M2. Okay, but now I claim that every ideal in Fx is of the form Im for some subset M. So let I be any ideal of Fx. Now I need to find a subset M of x such that I is of the form Im. Now before we do that, let's just make some observations about Im itself. So let's define delta x belongs to Fx by delta x of y is equal to x if x is equal to y and 0 if x is not equal to y. So this is the function which takes value, sorry, not x, it's equal to 1. It's a function which takes value 1 at x and takes value 0 everywhere else. And delta x, x belongs to x, is a basis of Fx, and moreover delta x, x not in M, is a basis of Im. Okay, so we'll keep these in mind and we'll keep this notation delta x also in mind. So now, given an ideal of Fx, we need to identify the set M for which it is of the form Im. As I said, every ideal of Fx is going to be of the form Im. That's what I want to show. So how would we find that set M? Well, if you think about it a bit, it's obvious. You let M be the set of those points in X such that f of x is 0 for all f in I. Right? If I were an ideal of the form Im, then certainly M would be the set where all the elements of I vanish. And now I want to show that I is equal to Im. Okay, so of course I is contained in Im. Just by the definition of M, right? Every element of I vanishes on every element of M. So it's enough to show that Im is contained in I. And for this, it's enough to show that delta x, where x does not belong to M, is contained in I. Because delta x, x not in M, is a basis of Im. Now delta x, so suppose x is not in M, then there exists f in I such that f of x is not 0. Right? Because M was a set of points where all the elements of I vanish. And then you can just look at the function f times delta x divided by the scalar f of x. Okay, so f of x inverse times delta x f. Now let's evaluate this at y. So if y is not equal to x, then delta x of y will vanish. So this will be 0 if y is not equal to x. And if y is equal to x, then you'll get delta x is 1, f of x is f of x, f of x times f of x inverse is 1. So if y is equal to x. So this is equal to delta x. Okay, so but I obtained it by taking f and multiplying it by some elements of the ring fx. So what we get is that delta x belongs to fx for all, not to xx, for to belongs to I for all x not in M, which implies now delta x, as x runs over elements not in M, span Im, so which implies that Im is contained in I. Hence we conclude that Im is equal to I. And so the conclusion is that every ideal of fx is of the form Im for some subset m of x. Okay, now here's an extra credit question for you. How much of this theory will hold if I allow x to be an infinite set? Okay, in this example, I've only taken x to be a finite set. So think about it. Example 2. Consider any field f and the ring of polynomials with coefficients in that field. Polynomials in the variable t, coefficients in f. So we've already seen that this ring ft is a Euclidean domain and therefore it's a principal ideal domain. So every ideal of ft is generated by a single element f. So the principal ideal generated by f for some f in ft. Also we know that the ideal generated by f is equal to the ideal generated by g if and only if f is u times g for some unit u of ft. What are the units of ft? The units of ft are non-zero constant polynomials. Or non-zero constants. Now recall, a polynomial is said to be monic if its top degree coefficient is equal to 1. Now given any polynomial, you can make it monic by just dividing it by its top degree coefficient, and therefore every ideal is generated by a monic polynomial. Moreover, if two monic polynomials generate the same ideal, then these two monic polynomials would differ by a unit, but that unit can only be 1 because both of them have the same leading term. So what we conclude is that ideals of ft are in bijection with monic polynomials. In ft. So every ideal is generated by a monic polynomial and that monic polynomial is unique. There's another ideal that we have which is the zero ideal. There's also the zero ideal which is generated by 0, which is technically not a monic polynomial. This is the only polynomial which doesn't have a leading term at all because it has no terms. So there's this one more extra ideal. Now you can ask, given two ideals I1 and I2, what are their sums and intersections? So what is f plus g and what is f intersect g? So for this, well, recall that f plus g, so what is f plus g? You can see that it's the same as the ideal generated by f and g. And this is a principal ideal. So it's the ideal generated by the GCD of f and g, which I explained to you how to compute in the section on Euclidean domains. And the ideal generated by f intersect the ideal generated by g is the ideal generated by the LCM of f and g, where you can define the LCM of f and g as just fg divided by the GCD of f and g. I'll leave you to think about these two and figure them out. Now let's take a special case of this example where f is an algebraically closed field. An algebraically closed field is a field where every polynomial can be written as a product of linear factors. So for example, you could take f to be the complex numbers. That's an algebraically closed field. Okay, so in this case, if f is algebraically closed, then every polynomial, every monic polynomial has decomposition f of x equals x minus lambda 1 to the power m1, x minus lambda 2 to the power m2, x minus lambda r to the power mr, where lambda 1, lambda 2, lambda r are distinct elements of f, and m1, m2, mr are positive integers. Okay, the set of roots of this polynomial are the numbers lambda 1, lambda 2, lambda r. These are the r roots of the polynomial, and mi is the multiplicity of the root lambda I. So we can define a multiset. A multiset is a set of the form, well, is an object of the form, which I will write like this: lambda 1 power m1, lambda 2 power m2, lambda r power mr, where so let's say a multiset in f, where lambda 1, lambda 2, lambda r are distinct elements of f, and m1, m2, mr are positive integers. And we can talk about the union and intersection of multisets. So if m1 and m2, so we can call this m. So if m1 and m2 are multisets, then m1 union m2 is the multiset lambda 1 raised to m1, lambda r raised to mr, where lambda 1, lambda r are the distinct elements that occur either in m1 or in m2. And mi is the larger of the multiplicities in m1 or m2, is the larger of the multiplicity of lambda I in m1 and multiplicity of lambda I in m2. Similarly, we can talk about the intersection of two multisets. m1 intersect m2 is the multiset lambda 1 m1, lambda r mr, where lambda 1, lambda r are the distinct elements which occur in both m1 and m2, and mi is the minimum of the multiplicity of lambda I in m1 and multiplicity of lambda I in m2. So now what we have is ideals in Ft are in bijection with multisets in F, and corresponding to the multiset lambda 1 m1 lambda r mr, you get the ideal generated by x t minus lambda 1 to the m1 t minus lambda r to the mr, the ideal generated by that. And so if we call this multiset M, we can call this ideal Im, and what we have is that Im1 plus Im2 is equal to Im1 intersect M2, and Im1 intersect Im2 is Im1 union Im2. So notationally very similar to the case of functions on a finite set, but with different meanings here. And we also have that if a multiset M1 is contained in a multiset M2. So what does it mean for one multiset to be contained in another? It means that the set of elements that occur in M1, they all occur in M2, and moreover, each element that occurs in M1 occurs with a multiplicity in M1 which is less than or equal to the multiplicity with which it occurs in M2. And what we have is M1 is contained in M2 if and only if Im1 contains Im2.